Stanford University.
Well, thank you, and thanks for this opportunity to introduce some subversive ideas about different ways to do and teach engineering. You may know that early this year, McKinsey came up with a revised supply curve for how much you save or pay in euros to abate forecast global greenhouse gas emissions in 2030 by various means that add up to 70% of the projected emissions. And you'll notice that the area under the profitable, that is negative cost, side of the curve for energy efficiency is nearly equal to the area under the right part of the curve for the more expensive supply measures, so that the average cost of that 70% abatement, they figured, is about 4 euros per ton of CO2. I'd like to talk about some innovations in how we combine energy-saving technologies or other resource-saving technologies to make this part of the curve even more negative cost, more profitable, and also go further to the right, saving a larger quantity of energy. In other words, if we count integrated design, the efficiency part of the curve gets bigger and cheaper. And there are two main stories around that, namely oil and electricity, each of which is responsible for a bit over 2/5 of the fossil carbon release. Let me just take an example, namely what's called here hybrid cars, which is a teensy little wedge there. When you drive your car every day, you're using effectively about 100 times its weight in ancient plants, very inefficiently converted to oil. But where does that fuel energy go? This is a design problem. It turns out that 7/8 of the fuel energy never gets to the wheels. It's lost first in the engine, idling, driveline, and accessories. Of the 1/8 of the fuel energy that does reach the wheels, roughly half is heating the air that the car pushes aside or heating the tires and road, and only the last 6% actually accelerates the car and then heats the brakes when you stop. But only a 20th of the mass you're accelerating is you. 19/20ths is the heavy steel car. Therefore, only a 20th of that 6% actually moves the driver, 0.3%. Not very gratifying after 120 odd years of devoted engineering effort. But the good news is that 3/4 of the energy needed to move the car, both the inertial and the rolling resistance terms, is caused by its weight. And every unit of energy we save at the wheel saves an additional 7 units that we don't need to waste getting it to the wheels. So there is enormous leverage in making the car radically lighter weight, whether with ultralight steels, light metals, or advanced polymer composites. That's what we used 9 years ago in designing this nearly quadrupled efficiency, uncompromised midsize SUV, which would have an extra retail price of $2,500 because it's a hybrid, but nothing because it's ultralight. Saving 53% of its weight turned out to be free. And the reason for that shows up when you look at the manufacturing. There are only 14 major parts in the body, each liftable with one hand and no hoist. In fact, the most complex loaded part on the side here I can briefly lift with one finger. And each of these parts is made with one low-pressure die set. A normal steel SUV has 10 or 20 times as many parts, each with an average of 4 progressive steel stamping die sets. So we just saved about 99% of the tooling cost. And the composite parts snap precisely together for bonding without the jigs, robots, and welders of the body shop. So you lose that, and also the paint shop goes away if you lay color in the mold. So there go the two hardest and costliest parts of making the car. And you end up with at least 2/5 lower capital intensity than for the leanest plant in the industry. By the way, the powertrain also gets 2/3 smaller. So it's the combination of the savings in tooling, manufacturing, and powertrain that pays for the ultralighting. And the technology is moving along very nicely. I brought my carbon cap today. This is a test piece from one of our spin-off companies for a military helmet that's now shipping, and it has quite nice mechanical properties. That kind of rings like a bell. You can beat it with a sledgehammer without hurting, and it's tougher than titanium. And I can pass it around if you're really careful to get it back to this corner in the next half hour. Where I have to go. Oops. Don't worry about dropping it. Actually, think of that little object as symbolizing a Saudi Arabia we just found drilling in the Detroit Formation, because that's how much oil the U.S. would save if we made all our cars and light trucks out of this stuff. And they get safer because this absorbs 12 times as much crash energy per kilo as steel. Half the weight, half the fuel use go away, and the car costs the same to make. Others have noticed this potential. Toyota, almost 2 years ago, showed a concept car called the 1X because it has the interior volume of a Prius, half the energy use and a third the weight, 420 kilos. And it's a plug-in hybrid with a little half-liter engine that tucks under the rear seat. Normally, such concept cars are dismissed as just a brag because they don't get to market, except the previous day, the world's biggest maker of carbon fiber, Toray, had announced a large factory to mass-produce carbon fiber car parts for Toyota. So putting the two together is clearly a statement of strategic intent, as they confirmed, and now Honda and Nissan have similar deals with Toray, so the next leapfrog is off and running. Well, this is all part of a much bigger picture of how to triple the efficiency of cars and trucks and planes by making them light and slippery with advanced propulsion, and often with better performance. For example, this concept car from Opel, a diesel hybrid, does 250 kilometers an hour and 2.5 liters per 100 kilometers, although not at the same instant. Much the same is true for planes, where you can save the first fifth of the fuel for free, as in the Boeing Dreamliner on the left, and 2/3 of the fuel going to blended wing body with a few years payback. In trucks, you can save the first quarter pretty much for free. Walmart already did that, and it doesn't have to look as exotic as this German aerodynamic truck to triple efficiency with about a half-year payback. There are also lots of big oil savings to be had in the buildings and industry that use the last 30%, but in those and in vehicles, the technology for efficiency is improving faster than even the stunning advances in finding and lifting oil, so efficiency keeps getting bigger and cheaper. It's much the same story in electricity. Back in the late 80s, my colleagues and I looked at the measured cost and performance data for over 1,000 technologies for saving electricity, and when we combined them and retrofitted them wherever they would fit and make sense and make money, they would together save about 3/4 of the electricity then used at an average cost that in today's dollars would be 1 cent a kilowatt hour. That's cheaper, of course, than running a coal or nuclear station, even if building the station and the grid were free. There were similar findings abroad. The utilities think tank found only a 40 to 60% saving potential, costing 3 cents instead of 1, but it turned out the difference was substantive. Was methodological, not substantive. And in any case, they're all big numbers, it doesn't much matter. As they would agree, the technologies keep improving faster than we apply them. So again, efficiency gets bigger and cheaper over time. It's as if the low-hanging fruit had fallen off the tree, it's mushing up around our ankles, it's spilling in over the tops of our boots, and the innovation tree keeps dumping more fruit on our heads. But this does not count integrative design. That's a whole other kind of innovation that's not about technology, but about how it is combined artfully to produce very unusual results. For example, if you were to come visit my house up in the Rockies, you'd find this structure, and it doesn't have to look like this to work like this. It's at 2,200 meters elevation, where the temperature sometimes goes to minus 44 Celsius. You can get frost any day of the year. You can get 39 days of continuous midwinter cloud. And yet, if you come into the central atrium, there you are in the banana jungle, where I'm now ripening banana crops number 29 and 30. And then you realize there's no heating system. Why not? Well, I didn't need one, and it was cheaper up front not to put one in. Huh? Well, if you ask most engineers how much insulation should you have in a 4,900 Celsius degree day climate, they'll say, use just the amount that will repay its extra cost over the years from the saved heating bill. This sounds reasonable, but it's methodologically incorrect, even though it's in all the textbooks. And it's incorrect because it leaves out the capital cost of the heating system. If you count that as well, you find that it's $1,100 cheaper in 1983 to put in super insulation, super windows, ventilation, heat recovery, and the like, and eliminate the heating system. So I then reinvested that money plus some more, totaling $16 a square meter, or 1%, in saving half the water, 99% of the water heating energy, and 90% of the household electricity, and all of that paid back in 10 months with 1983 technology. Today's, which we've just retrofitted, is much better. Here's a house that's comfortable with no air conditioning at 46C, and if built in reasonable quantity would be cheaper than normal to build and to maintain because there's no heating or cooling equipment. Here's a house actually modeled on mine, but in the opposite climate. It's in the steamy climate of Bangkok, Thailand, and yet it uses a tenth the normal air conditioning energy to produce superior comfort at exactly normal construction costs. And here on this campus is a wet lab, a very energy-intensive type of building that uses a fifth the energy allowed by the strictest standard in the United States, has exactly normal construction cost and very happy occupants, and gets over 50 units of cooling per unit of electricity. By the way, the performance could both have been improved. Those numbers could have been improved by another factor too, had the same engineer who designed the passive cooling system been able to design the circulation of the chilled water as well. So I give you these buildings, small is hard because they have a big surface to volume ratio, to illustrate how we can span pretty much the range of the Earth's climates with integrative design that makes big savings cheaper than small or no savings by optimizing the whole system for multiple benefits rather than isolated components for single benefits. Now, this is contrary to what we dimly remember from badly taught economics courses, which claimed there was a law of diminishing returns requiring that the more you save, more and more steeply the cost of the next unit of savings would rise until it gets too expensive and you have to stop. Many components don't even behave this way empirically. If you look at the actual data, since our motto in RMI is "In God We Trust, all others bring data," you find that this is not true, for example, for motors, industrial pumps, rooftop chillers, servers, refrigerators, televisions, and a lot of other things, but it is true of insulation. As I add more insulation to my house, I experience diminishing returns. But if I add maybe twice the amount that's normally considered cost-effective just based on the fuel savings, then I get to the point where I no longer need the furnace, ducts, fans, pipes, pumps, wires, controls, and fuel supply arrangements, and I end up $1,100 cheaper up front for a 99% saving. And why should I get there the long way around when I can tunnel directly through the cost barrier to that design destination by asking, is there a sensible way to design this building with no mechanicals? So that's one way to tunnel through the cost barrier. In the house cases I just showed you, we're saving energy cost and capital cost. We're optimizing for both of those, not just for one. And at the component level, it gets more interesting. The super windows have at least 10 kinds of benefits, not just one. Good ballast and motors have 18 each. The arch that holds up the middle of my house does 12 things, but I only pay for it once. There's a nifty part in the front of a Lotus Elise car that has 7 functions, but 1 cost. I think in my house there's hardly any component without at least 3 functions. And this yields quite consistent results across all sizes, programs, and climates. For buildings, for example, here's one in a cold climate where we pay extra for better windows and the like, but a lot less for the heating, ventilating, and air conditioning system, so the capital cost of the building goes down, and so does the energy use. Now, another way to tunnel through the cost barrier is to take advantage of retrofits you're doing anyway. For example, imagine a big glass curtain wall office tower, all glass and no windows, in a hot and cold climate, and the glazing seals are failing as they do after 20 years, so you have to reglaze the whole curtain wall. But instead of replacing it with the same dark heat-absorbing glass, let's use some spectrally selective glazings that are essentially perfect in letting in light without heat. They're also very well insulating, cost slightly more, but when we add that to deep daylighting and very efficient lights and plug loads, we can replace the big old cooling system with one 4 times smaller and 4 times more efficient, and $200,000 cheaper than renovating the big old one, which we have to do anyway for age and CFCs. So we end up saving 3/4 of the energy at a payback of -5 months. In other words, slightly cheaper than the regular 20-year renovation that saves nothing, just because we've coordinated and integrated whole building retrofit with the facade renewal and mechanical upgrade that need to be done anyway. The same thinking, of course, applies in industry. One of my favorite examples has to do with pumps. Pumps use the largest share of the world's motor energy, and motors use 3/5 of the world's electricity. We had a factory needing a heat transfer loop and helped a colleague redesign it to use 92% less pumping energy than the original supposedly optimized design, at lower cost, working better. And it wasn't because of changes in the technology, but because of 2 changes in the design mentality. The first was to use big pipes and small pumps rather than small pipes and big pumps. The friction in a pipe, of course, goes down as nearly the 5th power of its diameter. So how fat should the pipe be to optimize the friction? The engineering textbooks, at least in the English language, all say to make the pipe just as big as will repay its greater cost over the years from the saved pumping energy. Which again sounds perfectly logical, and again, it's methodologically wrong, because it leaves out the capital cost of not just the pumps, but the motors, the inverters, the electricals, all the pumping equipment has to be big enough to overcome the friction. And therefore, when we conventionally optimize the pipe as a component, we're pessimizing the system. If we optimize the whole thing, with the cost of the pipe going up only as the 2nd power of diameter, but the size of the equipment going down is nearly the 5th power of diameter, we will end up with fat pipes, tiny little pumps and motors, and the total capital cost goes down. Now the other change in design mentality was simpler and therefore more difficult. That's to lay out the pipes first, then the equipment. Normally we do it the other way. We put the tanks, boilers, and so on in some arbitrary, traditional, convenient place, and then ask the pipe fitters to come connect point A to point B, but by then A and B are far apart. Other stuff is in between. They're at the wrong height. They face the wrong direction. By the time the pipe makes it all the way across the space, all dressed at neat right angles like they teach us in trade school, the friction is about 3 to 6 times what it should have been with a straight shot. Now the pipe fitters think this is great. You pay them by the hour. They mark up a profit on the extra pipes and fittings. They're not paying for your bigger pumping equipment or your bigger electric bill forever after. But for you as owner, it would be more intelligent and beneficial to have fat, short, straight pipes, not thin, long, crooked pipes. You know, not rocket science, just good Victorian engineering rediscovered. And this 12-fold reduction in pumping energy and lower capex also had the bonus of saving 70 kilowatts of heat loss because it's easier to insulate short, straight pipes. But after it was done, we realized we'd messed up by not counting about 8 additional benefits. The whole system is now smaller, lighter, quieter. Those all have a value. It has a beautifully clean layout for easy maintenance access, but there isn't much to maintain, so your O&M cost goes down, your uptime improves, it will last longer because you don't have all those elbows being eroded away by fluid turning a corner, and you have more capacity for debottlenecking. So I did a rough calc that if we had properly counted those additional benefits, or at least the first 7, we would have saved another roughly factor 4. So we should have saved 98%, not 92, and it would have cost even less. Sorry, we'll do better next time. The more benefits you count, the better it gets. Another interesting thing about pumps, and it's the same principle that you saw already in cars, is that there is a chain of successive losses. If you start, for example, with 100 units of coal at the power plant, 70 units of enthalpy go away at the plant, you lose a bit more in the grid, and then there are all these compounding losses so that only 1/10 of the original fuel energy ends up coming out the pipe as flow. Now think about this backwards from right to left. Every unit of flow or friction we save in the pipe will save 10 units of fuel, cost, and pollution back at the power plant. Huge leverage. And it will make the upstream components smaller, simpler, and cheaper, so we'll save the most capital as well as the most energy. And it's not that hard. For example, how often in a building or a factory do we see a critical pump and an in-place spare pump, or two identical helper pumps? And they're almost always drawn like this, which is easy to draw, and then built like this, so that all the time the flow goes through two right-angle bends. That means friction, and usually 2 or 3 valves. Why don't we do it this way with no bends and no valves, or one valve? But we don't normally do it that way. When Peter Rumsey, however, in Oakland, did it in a retrofit, he saved 3/4 of the pumping energy by using fat, short, straight pipes, Y joints, a sweep bend, even a pipe running diagonally through the air as if it were a drain. You just need to remember, have the pipe fitters remember to lay out supply pipes as if they were drains. There's another part of their brain that knows how to do that. And of course, there's no reason to lay out pipes so they're easy to draw. The CAD does that for us. And there's no reason to make them look pretty. If they look pretty, they probably will not save energy and money. Well, we apply this kind of thinking, and very much more than that, in a wide range of applications. So in our latest $30-odd billion worth of industrial redesigns of facilities, we've ended up saving typically 30 to 60% of the energy on retrofits with a 2 or 3 year payback. And in new facilities, more, typically 40 to 90%, but with almost always lower capital cost. So, for example, our latest chip fab design is expected to use 1/3 the normal amount of energy, half the normal capital cost. Our latest data center improves the electric efficiency by a factor 16 with 10 or 15% less capital cost. Actually, if they felt able to do everything we recommended, they would have saved about a factor 80 on electricity and about half the capital cost. Our latest mine design uses no grid electricity and no fossil fuel. It runs on gravity. If you want to know how to do all this stuff, please go to rmi.org/Stanford, where you'll find my lectures in this engineering school 2 years ago, 30 years condensed to 7 hours at a high baud rate for buildings, industry, and vehicles. Of course, we couldn't achieve these kinds of results quite consistently if the stuff had been designed right in the first place. And I'm getting rather tired of redesigning stuff that wasn't designed right. So we're hatching a plot for the nonviolent overthrow of bad engineering. We call it 10xe, Factor 10 Engineering, described at 10xe.org, more about that later. Let me just give you one practical case, and that's the data center I just mentioned, which will be completed next month by EDS in the United Kingdom, now part of Hewlett-Packard. Just like in the pumping diagram or in the car, you start off losing a lot of energy. At least 2/3 of it goes away before it actually gets where you want it. But then half the energy delivered to the meter does not get into the servers because it's used in cooling and power supply and the like. And then half of what gets into the servers doesn't get into the chips because of inefficient, badly loaded power supplies and a lot of fans to take heat that shouldn't be there off the motherboard into the room so we can do dumb things with it. Then there is severe underutilization of resources. Many of the servers are doing little or nothing most or all of the time. And on top of that, we may even have bloatware, threads and processes going on that we didn't really want or need because of bad code and bad compilation. And we may even have inefficient business processes after that. So if you start downstream, the first thing you do is write terse code so that every compute cycle is a needed and wanted one. Then you buy servers 4 times as efficient, which does not increase their cost. Then there isn't much heat to take away, and there are more efficient ways to do that than to blow cold air at them. Also, there are better ways to do the power supplies, and you can even do a tri-gen fuel cell if you want to get rid of half the utility losses. So you start to see where that 2 order of magnitude leverage comes from, just by being very systematic and starting downstream. Well, this sort of integrative design is the key to many profitable solutions to things like climate change, oil dependence, global development. It's been successfully applied in hundreds of buildings, not counting over 20,000 passive houses in Europe. many industrial plants, many kinds of vehicles, and yet it is not yet in any official assessment, including those being written as we speak, and not for lack of telling them. It's not in any of our forecasts and policies. It's not in the foundations of our foreign policy, where we're still falling into the trap of supposing climate protection is costly when actually it's profitable. It's not yet in the textbooks, the courses, the curricula, or the mindset and practice of almost all designers. Boy, do we have a lot of work to do. This is a wonderful opportunity. And what we're therefore doing in partnership with Autodesk and others is to target how engineering is taught and how engineering is done, so we can use the engineering process and toolkit for radically increased energy and resource productivity. And we want, therefore, to make long-term structural changes in how engineering is done and taught through a casebook that lays out very clearly the design logic on facing pages of the conventional disintegrated design, like small pipes, big pumps, and the integrated design, so that by the time you've read to the bottom with the calcs and drawings, you understand how you got an order of magnitude different answer and how the efficient one was cheaper. And we figure from using these cases across all engineering disciplines and main applications that these do stick to the brain very well, and they will irreversibly rearrange the designer's mental furniture. So we're thinking about not just the casebook, but websites, network, and other ways of getting these tools into wide use. We are currently about here in a timeline where we are preparing several dozen cases which will be torn down and reconstructed, so that next summer we'll have several dozen leading practitioners and teachers of design putting this together into a vivid casebook with very strong heuristic flow, which we will then further refine and put out for beta testing initially to the sponsors. And we've already talked to many participants in different parts of the design value chain to help understand their needs and how best to speak to those needs. There are still some things we need and would cordially invite you to talk to us about supplying. We need working groups to be populated for preparing the cases. We have about a half dozen of those working. We need some more. We need best in the world practitioners and teachers for the summer study itself. We need outstanding cases, and particularly in the disciplines in which we have some gaps. I've listed those. We would like to have some seconded engineers to work in our banana farm during this winter. It's a terrible place, but somebody's got to do it. Or we could work virtually. We've already had one seconded engineer from ABB, and we're talking to several other people who would love to come help develop the cases. We need money, and there are good benefits in it for the practitioners. And we need suggestions for improvement of the methodology and content, and also how we get it into use through demand pull. For example, if you're a dean of engineering, once we have the beta version ready to distribute, we expect you will be getting a call from the chief executive of the firm that traditionally hires the largest number of your graduates, saying, sorry, we can't hire your graduates anymore unless you teach them in this new way, because they won't be able to produce the breakthrough results that our competitive success requires. And the many eminent deans that we've already involved in this exercise tell us, well, we've never had a call like that, but if we did, it would really get our attention. And we would probably change our pedagogy much faster than the traditional time constant, which is one funeral at a time. You can also expect to see say Harvard Business Review article which would cause business leaders to say, hey, there's this great new source of competitive advantage I just read about. It's kind of like Six Sigma or safety culture. Get me some of that. So we're thinking of all the cutting ways we can, and we'd welcome your suggestions on more ways to pull this sort of thing into the market. So if anything that I've said seems too good to be true, I would just invite you to reflect on the remark by Marshall McLuhan that only puny secrets need protection. Big discoveries and even odd things like my banana crop are protected by public incredulity. Thank you very much.
For more, please visit us at stanford.edu.